Today we will be focusing on the fundamental counting principle and permutations, our introduction to some probability topics out of chapter 11. We only do 3 different sections out of chapter 11. We'll start with 11.7 and then do 11.8, and then we'll come back around and get 11.1. So they are out of order. You should have already seen that from the MyMathLab assignments. In 11.7, we're going to talk about how many ways we can perform an experiment. So if an experiment can be performed in n distinct ways, and that's just a general number, could be any number of distinct ways, and a second experiment can be performed in n distinct ways, then those 2 experiments in that order can be performed in m times n ways. This is what I call my fundamental counting principle. Now, notice that I have 2 different experiments. Now, it doesn't have to be an actual experiment. The emphasis is on the fact that we have more than one set of options. More than one set of options. I have a first set of choices, and then I have a second set of choices. So more than one set is when I use the fundamental counting principle. For example, if we're at a restaurant, we're going to get the special. The special includes an appetizer and a main course. So anytime you order the special, you have to pick one appetizer, that's the first set of options, and one main course, that's the second set of options, or my first experiment, my second experiment, depending on which terminology you want to use. I have 3 different appetizers to choose from and 3 different main choices to choose from. Well, let's see. Let's say that my appetizers include salad, cheese sticks, and what else for appetizers? Or soup. And then my main courses, those options include a hamburger, a steak, or lasagna. Okay, how many different meals are available for me? Well, the first thing I have to do is choose an appetizer, and there are 3 different ways to do that. We're going to make what is called a tree diagram to show how many different ways we can choose. So first I have to choose an appetizer. I'm going to choose either salad, the cheese sticks, or soup for my appetizer. After I choose my appetizer, I also have to choose a main course. Well, if I picked the salad, I could choose the hamburger to go with that, I could choose the steak to go with that, or I could choose the lasagna to go with that. Same thing if I picked the cheese sticks as my appetizer. I can have a hamburger, a steak, or lasagna. If I got soup for an appetizer, I could have a hamburger, a steak, or lasagna, and each of those is a different meal. Salad and a hamburger is a different meal than cheese sticks and a hamburger, and that's a different meal than soup and a hamburger. So how many different meal choices are there? Well, if I wanted to do an organized list of these options, I see I have salad and hamburger. I have salad and steak, or I have salad and lasagna. I could have cheese sticks and a hamburger, cheese sticks and steak, or cheese sticks and lasagna. Or I could have soup and a hamburger, soup and a steak, soup and lasagna. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9 different meal choices. Did anybody notice that basically I'm saying I have 3 options for my first choice, and then each of those options has 3 more options for the second choice, for a total of 9 different meal choices. I can follow my branches, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can count my organized list options, or I could use this idea of the fundamental counting principle, that if there are m different ways for the first choice to happen and n different ways for the second choice to happen, then the total of my choices are m times n. So I had 3 different appetizer choices and 3 different main course choices for a total of 9 different meals I could choose. Let's do this for the next one. I'm not going to make you do an organized list or a tree diagram for this next example, but let's see if we can figure it out. So I go on a trip, all the clothes in my suitcase match. I packed 4 shirts, 2 pairs of pants, and 3 pairs of shoes. Assuming I'm going to put on a shirt, pants, and shoes for an outfit, how many different outfits can I pick? Well, I have shirts. I have to pick a shirt. I have to pick pants, and I have to pick shoes. According to fundamental counting principle, I multiply the number of ways I can choose each of those sets. Again, 3 different sets, more than one set of choices. How many shirt choices do I have? Well, I have 4. And then with each of those shirts, I have 2 different pairs of pants I could choose that are going to work. And with each of those combinations, I have 3 different pairs of shoes that will look good. How many different outfits is that? Well, 4 times 2 is 8 times 3 gives me 24 different outfits. And then we're going to reiterate it one more time, the definition of our fundamental counting principle. The number of ways in which a series of successive things can occur is found by multiplying the number of possibilities for each event. And we want to emphasize the fact that we use our fundamental counting principle because each event is a new or a different set of choices. Each event represents a different set of choices. My first event is picking a shirt. My second event is picking a pair of pants. My third event is picking a pair of shoes. My choices of a shirt are completely different than my choices for pants. And those choices for pants are not the same as the set of shoes that I'm choosing from. So each choice, each event, has a different set of choices. Let's practice this a little bit. When I don't have too many, I may ask you to give me an organized list or a tree diagram. For this first one, it says, at Pete's you can get 2 meals, hamburgers or tacos, and 3 drinks, tea, Coke, or lemonade. Create an organized list of the possible meal combinations if you get both a drink and a main course. So we're asked for an organized list. Well, I need to pick a meal and I need to pick a drink. My meal options are hamburgers or tacos. So if I pick hamburger, I can choose tea, Coke, or lemonade with that. So I can have hamburger with a Coke, hamburger with tea, or hamburger with lemonade. If I chose taco for my meal, then I could have taco with a Coke, taco with a tea, or taco with lemonade. So those are the 6, I can count them, 1, 2, 3, 4, 5, 6 different meal options, combinations where I pick a meal with a drink. And the way that I got that mathematically, when I pick a meal, there are 2 choices in that set. And when I pick a drink, there are 3 different options for that set. All right, my second example. At Mamma Mia's, there are 4 different drinks to pick from: soda, iced tea, water, or wine, and 3 main courses: pasta primavera, linguine with clam sauce, or spaghetti carbonara. This asks us to create a tree diagram this time of possible meal combinations where we need to choose both a drink and a main course. Now you can pick either one first. We're going to pick the drink first. And I'm going to need all my space. So we're going to say, okay, I've got 4 different drinks to choose from. So I need to have 4 main branches. My drinks include, I can have a soda, I can have tea, water, or wine. And then once I pick my drink, There are 3 different options for my main course: pasta primavera, linguine and clam sauce, or spaghetti carbonara. So for each of those drink choices, I have the same 3 meal choices: pasta primavera, linguine with clam sauce, spaghetti carbonara. There's my tree diagram. How many different branches does my tree diagram have? Well, it has 4 main branches, and then each of those main branches has 3 little branches off. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 possibilities. There are 12 different meal options if I get both a drink and a main course. Mathematically, how could we get there? Well, we see we have 1, 2, 3, 4 different drink choices, and we have 3 different main course options for a total of 4 times 3, or 12, when I use my fundamental counting principle. For problems 3 through 10, we're told to apply the fundamental counting principle to answer the question and do not list out each possibility. So we don't need to give an organized list or a tree diagram for the next few problems. But we do have different sets of choices, so we're going to be using fundamental counting principle. Now, I'm going to do the first one with you and kind of show you how I expect to see you set it up. And then I want you to pause the video and see how you can do on your own. A restaurant offers 4 drinks, 3 appetizers, 8 main courses, 2 desserts. If you get one of each, how many meal combinations are there? Well, my meal is going to include a drink, an appetizer, a main course, and a dessert. So I have 4 different sets to choose from. And fundamental counting principle means I'm multiplying. There are 4 drink options, 3 appetizer options, 8 main course options, and 2 dessert options. So how many different ways can I order? Well, when I multiply all of these together, I get 192 different meal combinations that are available. Okay, so again, I want you to pause the video. I want you to work through problem 10, problems 4 through 10, see how you do, and then come back and we'll talk about them. So for number 4, we have 3 different routes to pick. Our first route goes from A to B, our second route goes from B to C, and our third route goes from C to D. There are 2 ways to get from A to B, 4 ways to get from B to C, 5 ways to get from C to D, and 5 times 4 is 20, times 2 is 40. So there are a total of 40 different ways to make our journey. On number 5, be careful to make sure you're aware of what you're choosing. I have 5 different sets of choices here. The first thing I need to pick is color. Then I need to pick the type of transmission, then whether or not I have AC, whether or not I have power windows, and whether or not I have a CD player. It tells me there are 5 possible colors to choose from. So there are 5 choices in that set of options. I can either have standard or automatic transmission. So that's 2 transmission choices. Then you pick whether or not you have air conditioning, whether or not you have power windows, and whether or not you have a CD player. Do you see why each of these has 2 different choices? One is, for example, the AC, without AC, with power windows, without power windows, with a CD player, without a CD player. So there's 2 different ways to pick that. On number 6, we're talking about a license plate. In 2005, Texas license plates had 6 symbols, so I have 6 blanks to fill in because I have 6 different choices to make. The first 2 were numbers. Well, how many numbers are there? When you're talking about numbers, you're talking about digits. Look at your calculator. On my calculator, my digits go from 0 to 9, which is a total of 10 possible digits. So you have 0 and then 1 through 9, that's a total of 10 possible digits. So if the first 2 were numbers, that means I've got 10 possible digits here and 10 possible digits there. There are no restrictions. It doesn't matter if the same number is picked both times. So each time I pick a number, I've got 10 different numbers or digits to choose from. The last 4 symbols were letters, and our alphabet has 26 letters, A through Z. So I pick a number, pick a number, pick a letter, pick a letter, pick a letter, pick a letter. It doesn't matter if I pick the same thing twice, so we get to use repetitions. If I multiply all this together, I get 45,697,600. Sorry, I've got that funky looking 6 there. An easier way to look at this, to think about how to multiply it together so that I get it correct, I have 10 twice, so that's 10 squared times, and then I have 26 multiplied times itself 4 times, so 26 to the 4th power if I want to do it with exponents. Number 7 is a little tricky. How many 4-digit even numbers are there? So 4-digit number, that means that's why I have 4 slots. Assuming the digits can be repeated. Now, 4-digit even numbers. Now think about even numbers. What makes a number an even number? Well, even numbers are divisible by 2. So 8 is an even number, right? 12 is an even number. 354 is an even number. What makes each of these numbers even? Well, the ones digit is even. The ones digit is divisible by 2. So if a number ends in 0, 2, 4, 6, or 8, it's an even number. That's 1, 2, 3, 4, 5 different digits that I can pick from for this last slot. Does it matter about these other 3 digits? Well, no. In fact, they can all be odd over here. Odd or even, it's not going to matter. What matters, what makes it an even number, is this last digit, the ones digit. So I've got 10 different options to pick from for those 3 slots, just 5 for the rightmost or the ones digit. All right, number 8. Texas is always growing, right? So by 2009, instead of just 6 symbols on our license plates, now we needed 7 symbols on the license plates. The first 2 were letters. The third was a number. The 4th was a letter. And the last 3 were numbers. So that is what it would look like. When you're doing your homework and I ask you to show your work, this is what I mean by showing your work. I want to see how you figured out what values you were going to use to get your results. And then again, we could say 26 to the 1, 2, 3 third power and 10 to the 1, 2, 3 fourth power. Well, 10 to the 4th power lets me know I'm going to end with 4 zeros. 10 to whatever exponent tells me how many zeros will be at the end of the number. So what I really need to know is what is 26 cubed. If you want to work that in your calculator, remember your exponent button is this little housetop button right there above my x squared. I have to the any exponent. If I wanted to work that out, 26 cubed, I would say 26, that's the base, and then I raise it to the exponent 3. There's 26 cubed, enter. That gives me 17,576. And then I've got 10 to the 4th power. That tells me to put 4 zeros behind that amount. Okay, let's look at number 9. I'm taking a 10-question test. 10-question test means I have 10 blanks to fill in. Each question is true, false. So how many answer choices are there? Well, there's 2 different ways to answer each question. I can either answer it true or I can answer it false. So if I fill in all 10 of these blanks, I'm going to be putting a 2 all the way across, which means to multiply that out, I'm multiplying 2 times itself 10 times, which is 2 to the 10th power, or 1024. It's a lot easier to do this in your calculator than to try to keep track of how many times you've multiplied 2 times itself. Let's look at number 10. Now I'm taking a 5-question test, so I have 5 blanks to fill in. It's multiple choice this time, and each problem has 4 choices. So I'm filling in my blanks with 4s, which is the same thing as multiplying 4 times itself 5 times. Again, easier to input in my calculator. I also get 1,024. Notice that 2 to the 10th is the same result as 4 to the 5th. So my base is increasing by a factor of 2, and that reduces my exponent by that factor of 2. Okay, the second part of 11.7 focuses, instead of on the fundamental counting principle, on what we call permutations. When I'm talking about permutations, I'm talking about an ordered arrangement of a single set of objects. An ordered arrangement of a single set and of objects or people or choices or whatever I'm picking, symbols, numbers, I've just got one set. Now, ordered arrangement is important because with permutations, order matters. I only have a permutation if order matters. Again, I'm arranging only one set of choices. Determine if each scenario represents a permutation. If it's not a permutation, we need to say why it's not a permutation. And either way, we're going to figure out how many possibilities there are. An ice cream shop has 2 choices of cones, 4 choices of flavors, and 3 choices of toppings. Every order gets a cone, 1 flavor, and 1 topping. How many possibilities are there? Well, my first question, is this fundamental counting principle or is this a permutation? And the answer is in the number of choices, the number of sets of choices. Well, I am picking cone, flavor, topping. So I have 3 different sets of choices to make, which means I need to use fundamental counting principle. Permutations have only a single set of options. We have 3 sets of options. So I need to pick a cone, I need to pick 1 flavor, and I need to pick 1 topping. There are 2 different types of cones, 4 different flavor options, and 3 different topping options. So I have 24 possibilities as far as my order. Fundamental counting principle, because there's more than one set. Number 2 says a state uses 5 symbols for their license plates. The first 3 are numbers, the last 2 are letters. So I am picking 5 different symbols out of 5 different sets of choices. The first 3 are numbers, so 10 digits every time. Last 2 are letters, so 26 letter options. Doesn't say anything about repetition being a problem. I have fundamental counting principle, because I have different sets of choices. And I know that I'm going to end with 3 zeros because 10 times 10 times 10. So all I really need to know is what is 26 or 26 squared to figure out the result. And 26 times 26 is 676. When I put the 3 zeros behind that, I have 667,000 possible license plates. What about number 3? A comedian has 6 jokes. How many different ways can he order his routine? Well, I only have 1 set to pick from. When I only have 1 set and I'm interested in an ordered arrangement, that is a permutation. I'm going to tell all 6 jokes, but the order I tell them in makes it different. So since I'm going to tell all 6 jokes, I need 6 blanks. 1, 2, 3, 4, 5, 6. The first joke, I have all 6 to pick from. So I have 6 jokes to choose from. Let's say I tell the one about the dog. How many jokes are left? Well, there's 5 jokes left to pick for the second one told. And I tell the one about my child. And then there's only 4 jokes left to pick from. And I tell the one about the priest and the rabbi that went into the bar. And then there's only 3 jokes left to choose from. And I pick one of those. There's only 2 jokes left. And for that final joke, there's only 1 left that is possible to tell. So I need to multiply 6 times 5 times 4 times 3 times 2 times 1. That gives me 720 possible arrangements of those 6 jokes. It's a permutation, an ordered arrangement, because I only have one set to pick from. Each time I pick something, that means there's one left thing to choose the next time around. Look at number 4. There are 15 members of the film club, and they need to pick 4 officers, a president, a vice president, a secretary, and a treasurer. So how many sets of people am I picking from? Well, I'm just picking from one set. There are only one film club with 15 members, so it is a permutation. Now, order matters here because I'm picking officers. The president's job is not the same as the vice president's job, and it's not the same as the secretary or the treasurer. They each have a unique position, so the order matters. I'm only picking 4 times, not like the jokes. I told all 6 jokes, so I had 6 slots to fill. For this problem, I'm only picking 4 different officer positions. I'm picking president, vice president, secretary, and treasurer. Once you've been picked for a position, you're not available to be picked for another. There are 15 club members, so I have 15 options to choose for president. I choose Jose for president. Well, now there's only 14 members available to be picked from for vice president, and I choose Sally for vice president. What about secretary? How many club members are left? Well, there's only 13 club members left to be selected as secretary, and I pick Bill. And then treasurer, there are 12 different club members left who can be treasurer. So my order matters. I have a single set. That's the 2 things that make this a permutation problem. I multiply 15 times 14 times 13 times 12. I get a total of 32,760 different ways I can pick the president, vice president, secretary, and treasurer from just 15 club members. That's a lot. Now, permutation, you'll notice if you look at your formula sheet, the permutation formula is much more complex than what we're doing. We do kind of a simplified version. You're welcome to use the permutation formula, and we'll talk about it here in a little bit. But I usually just do the simplified version of calculating permutations. Let's look at the next page. It says to solve the problem numbers 1, 2, and 3. For the first one, 5 singers are performing. How many lineups are possible if each singer performs once? I've only got one set of choices. All of them are going to sing, so I have 5 different blanks to fill in, 5 spots, 1, 2, 3, 4, 5. How many lineups can I do? I've got an ordered arrangement of one set, so one set, order matters. That makes this a permutation problem. I've got all 5 singers to pick from for the first singer. Then that first person has sung. There's only 4 people left who can go second, and then 3 people left who can go third, 2 people left who I can choose to go fourth, and then we've got that one last person who has to go last. When I type this into my calculator, 5 times 4 times 3 times 2 times 1, I get 120 different ways I could line up those 5 singers. In the example above, one of the singers insists on being last. So let's look at this. We still have 5 people who are going to sing. 1, 2, 3, 4, 5. But let's say that Alex insists on going last. So I only have 4 slots to fill now, and I only have 4 singers to pick from. So now I have 4 people who can go first, 3, 2, and 1, because I already know that Alex is going to sing here. So this time it's still a permutation, but it's 4 times 3 times 2 times 1, which comes out to be just 24 different ways to line them up. All right, number 3, you have 10 different books. How many ways can you arrange them? Well, hopefully you've kind of got the gist of it. We're arranging all 10 books. I've got one set, so it's an ordered arrangement. I've got I'm going to start with 10 and I'm going to work my way down all the way until I get to 1, right? So 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Oh, I squished it in. Sorry, I got ahead of myself. I'm multiplying all those factors together from 10 to 1. Type that into your calculator. Hopefully, you will get 3,628,800. As we get more numbers to multiply, it gets easier and easier and easier to make a mistake. So I want to introduce you to something on your calculator called factorial notation. Now let me give you the definition of factorial notation, and then I'll show you how to apply it to these problems. Factorial notation, you're going to know you're given a factorial if you have an exclamation point. So in factorial, in exclamation point means in factorial. What I'm going to do when I have a factorial, I start with whatever this number is, and then I count my way down all the way to 1. So I'm multiplying things together from whatever number I'm starting with to 1, and that is in factorial. I need to put an equal sign here. Now by definition, I'm going to tell you that 0 factorial is defined as 1. But in factorial would be start with n, multiply your way down to 1. So 12 factorial, I would start with 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Basically, that's what I've done here, right? I had 10 books. I counted my way down from 10 to 1. That's the same thing as 10 factorial. Here I had 4 factorial, and here I had 5 factorial. So that's the notation. Well, how does that help us? That helps us because we have a factorial button on your calculator. All right, so on your calculator, find the probability button, PRB, right there. When you turn your calculator on, if you will type in, for example, let's do 10 factorial. 10, and then push the probability button, go across until you get to that exclamation point. So you're going to use your arrow and move it across until that exclamation point is selected, push enter. And here you have it, 10 factorial notation. Hit enter again, and it gives you your result. So I want you to take a second and go ahead and do 4 factorial and 5 factorial using the probability button so that you practice it. So 4, and then I push probability. I'm going to have to move it over to select the exclamation point again. There's my notation, 4 factorial. I get my result of 24. Practice it using 5 factorial. And then we're going to move on and we're going to talk about simplifying some things in order of operations. Now, I want you to understand what a factorial does, as well as know how to use that factorial button. Sometimes it's faster just to do 4 times 3 times 2 and then times 1 doesn't really change anything than it is to pull up that notation for factorial. However, if you get up here to larger numbers, it's a lot faster to use your factorial button. All right, order of operations with factorials. Make sure that you're following correct order of operations even when you are doing a factorial problem. For example, multiplication is more important than subtraction, right? Our order of operations is parentheses and exponents first, then we multiply and divide from left to right, and then we add and subtract from left to right. So multiplication and division is more important. It comes before addition and subtraction. This is a multiplication problem. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So I need to calculate each of these factorials before I do the subtraction. 7 factorial, if I use my calculator, comes out to be 5,040. There's an airplane passing over. Loud out there. Minus 3 factorial is just 3 times 2 times 1. So that's just 6. I can do that easily in my head. But the important thing here is that the correct answer, the correct result, is 5,034. That is a different order of operations than this next problem where I have 7 minus 3 in parentheses. Parentheses and exponents have first order importance. So I perform what's inside the parentheses. I simplify the parentheses first. 7 minus 3 is 4, and then I do my factorial. 4 factorial, I really don't need my calculator for, because I can do that in my head, or I can do it just by typing in the numbers. 4 times 3 is 12, times 2 is 24, and then times 1 doesn't ever change anything, right? Let's look at this third problem across. What comes first? What is your first order of importance? Do you apply the factorial or do you do the division? Well, we work inside the parentheses first, so that we will do the division. 12 divided by 4 is 3, and then I have 3 factorial, which is just 3 times 2 times 1, which is 6. Over here, what am I going to do first? Well, I need to do the factorials first before the division. Now, this problem, I'm going to show you how to simplify, and I want you to take careful note. You can expect to see a problem like this with factorials that I want you to simplify by hand on the exam. So I want you to make sure you understand how to simplify factorials. The first thing we're going to do is set up the numerator and the denominator. 9 factorial starts at 9 and goes all the way down to 1. 6 factorial starts at 6 and goes all the way down to 1. What do you notice about this problem? Well, I have common factors in my numerator and denominator. 6 times 5 times 4, which is basically 6 factorial, right? 6 factorial over 6 factorial. Anything over itself is 1. All of that is going to cancel out. It's going to divide to 1. And what I'm left with is just 9 times 8 times 7, which is 504. A simpler way to simplify this, instead of having to write all of that out, would have been to say, okay, my denominator is 6 factorial. So I know I'm going to cancel that. My numerator will be 9 times 8 times 7 times 6 factorial, instead of having to write it all out. And then I see that anything over itself is 1. So I'm just left with 9 times 8 times 7. So either one of these is a correct way to show how to simplify that problem. I do need you to know how to simplify that problem. And this next expression is a perfect example of why you need to be able to simplify. I want you to do 104 factorial in your calculator. Let's say we weren't going to simplify. You're going to do 104 factorial in your calculator. Well, when I type it in, I type in the 104 and I use my probability button to bring up that factorial notation, 104 factorial. And when I push enter, I get an overflow error. Basically, that means this number is too big. I can't show it to you with my calculator because it's just too much. It doesn't work. Well, how can I get around that? I get around it by simplifying. Just like I knew that my denominator here was 6 factorial, that was all going to divide out. Well, here my denominator is 102 factorial. That is all going to divide out because my numerator, the top number, is bigger. My top number starts with 104 times 103 times 102 factorial. Those match. That means everything from here on is going to cancel out and give me 1. All I'm actually left with is 104 times 103, and when I type that into my calculator, I get 10,712. That is how we simplify factorials. Let me give you a couple of, go ahead and do this one. Do 29 factorial divided by 24 factorial. Keep in mind, you're going to cancel out or simplify what matches. Well, what's going to match up? This 24 factorial, because it's in my denominator, it's less than my numerator. So I know when I get over here to 24, that's going to divide out. my numerator just has to get from 29 to 24. So 29, 28, 27, 26, 25, and then my 24 factorial is going to divide out or cancel out and divide to 1. And I'm left with 29 times 28 times 27 times 26 times 25, which comes out to be 14,250,600 when you type that into your calculator. I'm going to give you a couple more to practice on how to simplify factorials, and these are a little bit smaller. You could do these pretty easily in your calculator, but I want you to show me how to simplify these two factorial division problems. Pause your video, work them out, and then come back. All right, so for these two problems, this is what you should have written, what I have in red, and then you can show me that, look at that, that cancels out, and I'm left with 7 times 6 times 5. 6 times 5 is 30, and 30 times 7 is 210. For the second problem, that 3 factorial is going to cancel out and leave me with 5 times 4, or 20. All right, let's look at this last page of notes and talk about dividing out duplicates. When I have duplicate values, duplicate symbols, duplicate letters, duplicate numbers, whatever I'm duplicating, I want to make sure that I divide out the repetitions. Divide out the repetitions. Now what this looks like in terms of a formula would be n factorial over n sub 1 factorial times n sub 2 factorial, where these values in my denominator represent the number of repetitions. Now don't stress about this. I'm going to show you how it works. These next 3 problems, A, B, C, all work with dividing out duplicates. So let's look at A. It says, how many ways can you rearrange the letters or numbers of Tallahassee? Well, when I count the letters in Tallahassee, I see that I have 11 letters. So that's how many things I need to arrange. I need to arrange those 11 letters. So that gives me an 11 factorial. But I also notice that I have repeated letters in that word. A is repeated. Look at that. I have 1, 2, 3 A's. So that would be 3 factorial representing those A repetitions. And then I have an L that's repeated right there. I have 2 L's. So that would be 2 factorial to represent the L that's repeated. I have 2 S's. So that's another 2 factorial for the S repetitions. And then finally, I have 2 E's. So that is yet another 2 factorial for that E that is repeated. Okay, so how can we simplify all of this? Well, there's a couple of different ways to look at it. I could do all of 11 factorial as my numerator, multiply out each of these and make that my denominator and then divide. But let's simplify. In my denominator, I have 2 factorial, 2 factorial, 2 factorial, 3 factorial. 3 factorial is the biggest value. So I know I want to stop there. In my numerator, I'm going to say 11 all the way down to 3 factorial. 11 all the way down to 3 factorial. There's that 3 factorial. That's going to cancel out. Well, what else do I have in my denominator? I have 2 factorial, 2 factorial, 2 factorial. Now, 2 factorial is 2 times 1. Does it change anything when I multiply by 1? It does not. So for simplicity's sake, I'm just going to write this down as 2 times 2 times 2 instead of 2 times 1, 2 times 1, 2 times 1. So that would be 2 times 2 times 2 for those 2 factorials. Okay, I see my 3 factorials cancel out. That's 1. What else will cancel out or simplify? Well, 2 times 2 is 4, times 2 is 8. So these 3 2's multiplied together cancel out with that 8. And I'm left with 11 times 10 times 9 times 7 times 6 times 5 times 4, which is still kind of a lot to multiply together, but I simplified it as much as possible. So when I divide out the duplicate letters and recognize that L, this first L and the second L rearranged look the same, I get 831,600 different ways to arrange the letters in Tallahassee. Okay, let's do Mississippi and divide out duplicates there. All right, so Mississippi. How many letters are there in Mississippi? Well, again, I have 11 letters. So I'm going to do 11 factorial as my numerator. And then in my denominator, I need to look for those repeated letters. The first letter I see that repeats is I. And I have 1, 2, 3, 4 I's. So that is 4 factorial representing those repeated I's in my denominator. And then I see that I have an S that repeats. I have 1, 2, 3, 4 S's that repeat. So that's another 4 factorial in my denominator. And finally, I have that P that repeats. And there are only 2 P's. So that's a 2 factorial in my denominator. Okay, let's write this out and simplify. There are various ways to show the simplification. The important thing is that you remember when you have a factorial that represents, for example, 4 factorial is 4 times 3 times 2 times 1, not just 4. Okay, I've got a 4 factorial, 2 factorial in my denominator, so I'm going to stop at that 4 factorial. So my numerator, I count down from 11 to 4 factorial. So there's a 4 factorial that's going to divide out. I have another 4 factorial and a 2 factorial. So my 4 factorial here would be 4 times 3 times 2 times 1, right? And then my 2 factorial is again 2 times 1. I'm not writing those times 1s down because I don't need them there. These 4 factorials cancel because anything over itself divides out. It's a factor of 1. What can I do with this? Well, I have some options. I could just say 4 times 3 is 12. Times 2 is 24, times 2 is 48, and then multiply out my numerator and divide it by 48. I could do some further reductions here. Either way is fine. 3 times 2 is 6, and there's a 6. Let's go ahead and cancel that. 3 times 2 is 6. That cancels with that 6. 6 over 6 is just 1. Then I have 4 times 2, which is 8. 4 times 2 is 8, and there's an 8, so that cancels out. What I'm left with here to multiply is 11 times 10 times 9 times 7 times 5. And when I multiply that out, I get 34,650 different arrangements of the letters in Mississippi. All right, my last example here gives numbers instead of letters. I've got 1, 2, 3, 4, 5, 6, 7 total digits. So let's do 7 factorial in my numerator. What digits repeat? Well, my 4 repeats. I have 2 of them. So that would be 2 factorial representing those repeated 4s. And my 6 repeats, and I have 4 of them. So that would be 4 repetitions of that 6. When you pick a way to simplify this problem, hopefully it will look something like counting down to my 4 factorial, and then I also have this 2 factorial, which is basically 2 times 1. Recognizing that 4 factorial over 4 factorial is just 1. And then I can do this multiplication in my numerator and divide it by 2. Or I could go ahead and say, you know what, 6 divided by 2 is 3. So 6 divided by 2 is 3. My numerator becomes 7 times 3 times 5. Which is 105. 105 different ways to arrange those digits. Okay, here we get to our actual definition of permutation. This definition of permutation you're going to see in different textbooks. You're going to find it online. It is a more complicated way of finding the permutations, but you're always welcome to use that definition. My definition of permutation is, I always say in pick R. I'm starting with in things. I'm going to pick permutations of R of them. So for example, when I had my 15 club members and I was picking 4 officers, N would be 15, R would be 4. Let's write out the definition and then I'll show you that example. My definition is N factorial over N minus R factorial. So here's what this looks like as an example. If I have, let's go back and find that problem when I introduced permutations. Okay, here we go. Back on the 4th page of our notes, on number 4 actually, we had 15 members of the film club. We picked 4 officers. We did 15 times 14 times 13 times 12 and got this total of 32,760 because of this. That is a permutation problem. Here's how we work with permutations. According to the definition, I have N is 15 because that's my total group I have to choose from, and I'm going to pick 4 of them in order. Order is going to matter. If I plug that into my definition, my numerator is 15 factorial because N factorial. My denominator is 15 minus 4 in parentheses and then factorial. Well, order of operations, I need to work inside parentheses. So that gives me 15 factorial over 11 factorial. And then as I showed you how to simplify things out, I'm going to start in my numerator at 15 and I'm going to stop at 11 factorial, right? 11 factorial. That 11 factorial over itself is just 1. So what am I left with? Well, I'm left with exactly what we did in our problem on number 4, 15 times 14 times 13 times 12. 15 times 14 times 13 times 12 comes out to be 32,760. 32,760. So my definition, my formal definition of factorial sets me up to get what I was doing before, where we just start with our number. We figure out how many blanks to fill in, how many ones to pick, how many times to count down. You are always welcome to use the formal definition of permutation. I'm a little lazy. I like to do it the easy way, but I do want you to use this factorial or this permutation notation. So for example, 6 cars race and there are no ties. How many ways can the first 3 finish? So I have a total of 6 cars, that's N. And I'm interested in the first 3 finishers. That's R. That's how many times I'm interested in picking. So my notation in pick R, in permutations, choose R, would be 6, pick 3. I can plug this into my formal definition, or I can say, you know what? I'm picking 3, so I've got 3 blanks to fill. My first pick, I have 6, and then I've chosen one, so there's only 5, and then I've chosen another one, so there's only 4. 6 times 5 times 4. I start with 6, and I count down 3 times. 6 times 5 times 4 is 120. That's not bad, right? All right, show permutation notation for the next problem. A DJ has 13 records. He plays 7. So he has a total of 13. That's my N. He is picking 7 of them in order to play. So what does that look like? Well, I have 7 blanks to fill in. 1, 2, 3, 4, 5, 6, 7. My first blank, I start with 13 and I count my way down until I have picked 7 times. So I've counted my way down from 13. What do I get? Well, plug that into your calculator. Multiply out all those factors. You should get 8,648,640. And that was a lot, right? That's a lot of opportunity to make mistakes. We can fix that. Pull out your calculator and let's go back to that probability button. Hopefully when you were doing your probabilities, you noticed that there were options other than, we had to move past some options to get to our factorial, our exclamation point. we're going to use this permutation option under probability. So we're using our probability button again. Type in n. In this case, n is 13. Now I need permutations, so I'm going to pick probability. And notice that that is the option that's right up first, n pick r. So I hit enter and it pulls in this notation for me. I've got n, I'm telling my calculator I'm doing permutations. Now I need to enter r. In this problem, r is 7. Enter and it gives me the correct result. Now I want you to practice using this permutation button by doing 6 pick 3. 6 permutations, choose 3. Make sure that you get 120 as your answer. And then do this last problem. We have 20 favorite movies we are going to rank. So that means in order, order matters, our top 3. Now this is pretty easy to write down. 20 times 19 times 18. It would probably actually be quicker just to multiply 20 times 19 times 18 and get 6,840. I want to encourage you to practice using your permutation button on your calculator and make sure you know how to do that.